In this video, we're going to be moving from the world of the wheel to the quantum world of the atomic nucleus. To help us develop some ideas behind the quantum behaviour of atomic nuclei, I prepared some slides here, which we'll go through in turn. I'd hate you to think that this is what an atomic nucleus looks like, but we need to use some symbol to represent our nucleus, and a blue ball is as good as anything. A blue ball with a vector to represent the direction of the angular momentum and the magnetism. And in a magnetic field, the lowest energy state is with the magnetic dipole of the nucleus aligned with the magnetic field direction. We use the words spin or angular momentum and magnetic dipole moment interchangeably when it comes to direction. In this set of videos, we'll be exclusively concerned with the hydrogen nucleus known as the proton. It has two possible quantum states in the presence of a magnetic field: spin up and spin down. We've seen spin up already, it's the low energy state. Spin down is the high energy state. And in general, being quantum mechanics, it's possible to have a coherent superposition of these states in which one nucleus is both spin up and spin down simultaneously. That's the superposition that applies when we're observing protons precessing in a magnetic resonance experiment. But don't be worried if you don't know quantum mechanics. We can explain all we need to for this video series without ever again talking about superposition states. But if you really want to understand NMR deeply, and all that's possible with nuclear magnetic resonance, then you really do need to know this quantum mechanical stuff quite deeply. What I want to do in this set of slides is to introduce the idea of what happens when we have lots and lots of nuclei in thermal equilibrium with a magnetic field. First, we need the idea of temperature, and we use a little thermometer symbol on the bottom right to indicate temperature. So let's look at what happens at finite temperature. Thermal energy means that not all nuclei will be in their low energy state. In fact, there's a proportion in both the high and low energy states, with a preponderance in the lower energy state. Note that these thermal equilibrium states are not superposition states. Each nucleus is definitely in either up or down states, but there is a slight preponderance of up, the lower energy state. The ratio of populations in each state is given by the Boltzmann factor, which in turn depends on the ratio of the thermal to the magnetic energy. At room temperature in laboratory magnetic fields, the thermal energy is much greater than the magnetic energy, so that means the populations are nearly equal. However, that slight preponderance in the lower energy state shows up as a spin excess. It's the spin excess that's visible. All the remaining spins cancel out their angular momentum and magnetism and are invisible in nuclear magnetic resonance. We can increase the spin excess by lowering the thermal energy, in other words, by reducing the temperature. At absolute zero, all the spins will be in the low energy state and the spin excess will be at its maximum. But that's not too practical for many samples, humans undergoing an MRI scan, for example. But we do see that the magnetisation vector grows as the spin excess in the low energy state grows. Let's go back to room temperature. There we are with a small spin excess again. But another way to increase the spin excess is to keep the temperature fixed and increase the field. This way we increase the magnetic energy while the thermal energy remains fixed. Here we're going from 2 Teslas to 9 Teslas and then back down again. But even if we're restricted to weak fields and room temperature and our spin excess is very small, remember that there are vast numbers of nuclei in our sample. And even if only a small fraction are in the spin excess, the total number could be quite large. So let's take our thermal equilibrium magnetisation and see what we can do using the nuclear magnetic resonance trick. Just like our wheel in its low energy state, where precession was invisible, we have the magnetisation pointed along the vertical axis, and we need to reorient the nuclei. Once we do that, the precession will be visible. We call this precession after the physicist who first predicted it. It's called the Larmor precession, and the frequency of precession is known as the Larmor frequency. Note on the top right-hand part of the slide the equation which tells us the precession frequency. It's the most important equation in NMR and MRI. It says that the precession frequency is proportional to the field The constant of proportionality, gamma, depends upon the nature of the nucleus. That gamma is sometimes called the gyromagnetic ratio or the magnetogyric ratio. Hydrogen nuclei have the biggest gamma and are the most sensitive nuclei to be used for NMR and MRI. Finally, note the use of a coil to pick up the induced voltage from the precessing spins. This constitutes our free induction decay signal in NMR. Let's summarise some important ideas from these slides. First of all, the strength of the magnetic field determines the amount of magnetisation that we have when the atomic nuclei are in thermal equilibrium. Second, the strength of the magnetic field also determines the precession frequency of the atomic nuclei. The higher the field, the higher the precession frequency. And the third idea we see is that we need to have a coil that's used to produce an oscillating magnetic field in resonance with the nuclei that causes that torque which tips the magnetisation out of equilibrium into the transverse plane. The same way that with the wheel I used an applied transverse torque moving around with the precession of the wheel to reorient it. And that same coil is used not only to transmit to the nuclei but also to receive the signal, to pick up that electromotive force, that oscillating voltage, as the nuclear magnetisation precesses around in the coil, with the signal gradually decaying away with time as the spins come back to thermal equilibrium, and we call that signal which decays with time the free induction decay.